Hello, everybody. In this episode, I'll be speaking with Mark Xu. Mark is a researcher at the Alignment Research Center, where he works on mechanistic anomaly detection, which we'll be speaking out during this interview. He's also a co-author of the paper Formalizing the Presumption of Independence, which is about heuristic arguments, a way of formalizing, essentially, what a mechanism is. For links to what we're discussing, you can check the description of this episode, and you can read the transcript at axrp.net. All right, so I guess we're going to be talking about mechanistic anomaly detection. First of all, what is that?
Yeah, so I think we can start with a more basic thing, which is what is anomaly detection? So there's this traditional problem where, say, you have some factory making some widgets, and you want to decide whether or not a widget is a bad widget, and you don't really know what a bad widget is, but you do know that the average widget is a good widget. So you can do something where you measure some various parameters of your average widget, or you measure some various parameters of every widget, and then you maybe do something simple where you're suppose a widget is more than a few standard deviations along two or more of my measurements. We're going to call that a quote-unquote anomalous widget, and we're going to not sell that sort of widget. I think that's the sort of standard conception of what an anomaly is, and what it means to sort of detect anomalies is to get rid of things that you think are not good or anomalous. And then there's another thing that we want to do, which is so you have some system that's, instead of making widgets, it's doing certain kinds of reasoning. And we're interested in this general question of so we have our ML system, and we have a data set on which it's not exactly making widgets that we think are good on average, but it's doing reasoning that we think is good on average, because of our ability to create the training set and measure various properties of the training set, et cetera, et cetera. And then we're worried about situations where, say, off distribution, it starts doing things that we don't think are good, but in ways that we can't quite measure the thing that's not good. And so we want to do anomaly detection, but we can't quite do it in terms of measurements that we can actually make. So we want to do it with respect to the kinds of reasoning that our system is performing. And we call that sort of mechanistic anomaly detection, where the idea is, instead of being anomalous in terms of what the system actually does, it's anomalous in terms of the mechanism it uses to do the thing that it's doing, if that made any sense.
Yeah, so I guess my understanding is you have your AI system, and it's in the lab, you've tested it, and it didn't do anything obviously horrible. And so you're sort of ready to release it, but you're wait, one of my AIs in the real world, I'm going to I'm going to detect when it does any kind of reasoning that's really different to the kind of reasoning that it did before. And then if it does a really different kind of reasoning, I guess I'm going to try to shut it down or something.
Yeah, I think the thing that happens after that is a bit confusing. I think the standard thing I think of is we're going to take it offline and retrain it on the kind of thing where it did a bad thing, and try to get it to not do that bad thing anymore. But I think that's roughly right. Yeah, I'm tempted to try to explain it again, because I feel I didn't quite explain it that well.
Sure.
Yeah, so I think the situation is you have some ML system, and you have some set of scenarios in which it's doing a thing that you think isn't going to be catastrophic for human interests. It has murdered 0 humans on a particular training set. And then you're okay, that gives me some amount of belief that it's not going to murder any humans off distribution. But the problem is, I don't have this guarantee that the way it acts off distribution is in any way the same as the way it acts on distribution, where maybe the standard deceptive alignment example is where your AI is constantly scheming and checking, will I get away with murder? Will I get away with murder? And then on training, the answer is always no. And then off training and on deployment, it finds a situation where it could get away with murder, and then it murders all the humans. And that is no good. And so the thing we want mechanistic anomaly detection to be able to do is to provide some sort of guarantee that the way that your system is generalizing off distribution is employing the same kinds of reasoning or the same kinds of mechanisms that it's employing on distribution. And so your ability to measure whether or not your AI murders all humans applies off distribution now, because you have this, you sort of fingerprinted the kinds of reasoning that it's doing on distribution, and you're ensuring that it's doing the same kinds of reasoning off distribution, or if it's not, you're like taking it offline. And so long as it's doing the same kinds of reasoning off distribution as it's doing on distribution, and you have this ability to measure how good the reasoning it's doing on distribution in terms of measuring like the consequences of the way it's acting, then hopefully you have some sort of guarantee that off distribution it won't like murder all the humans.
Okay. And like the reason this is better than just like checking if it in fact murders all the humans is like hopefully the reasoning first you plan to kill all the humans and then you actually do it and anomaly detect the first one and then just like stop that from happening before the plan actually proceeds. Is that roughly right?
I think that's one reason. I think another reason is like you can imagine situations where your AI like murders all the humans and there's like no sensor reading that would tell you this fact. So it's like simultaneously conspired to like hack all the heartbeat sensors to make them like keep pretending that humans are alive and like hack all the cameras to make them keep showing happy, healthy humans, et cetera, et cetera. And so there's just like, even if in theory all the humans are dead, there's no way that you can like tell that all the humans are dead. And so
where you is, I guess, the computers.
Yeah, or just like
I could tell.
Sure, all sensors, or like suppose that there was one human still alive, trapped in like a box, and they had access to like every, sensor that humans ever made. They would be like unable to tell whether or not the humans were alive or dead, and that's no good. And the hope is like we can avert those kinds of outcomes also by checking whether or not like the AI, quote unquote, knew that the humans were dead because it was like employing kinds of reasoning that involved stabbing all the humans versus not stabbing all the humans, or kinds of reasoning that implied that stabbing all the humans were good versus kinds of reasoning that implied that stabbing all the humans were not good.
So I guess what I'm hearing is that it seems like the hope is to solve two problems that I guess the alignment community have sort of separated, where one problem is like you can set up some like scheme for sort of rewarding your AI for various like measurable properties of the environment, like, on this camera feed, does it look like all the humans are alive? Like, do the humans write down on pieces of paper, I like what this AI is doing? And like one problem is your AI could like your AI is just never motivated by those things, and later it just like disregards all those signals and just like does whatever it wants, even though the humans don't like it and even though it stops like humans from appearing to be alive. And then like another way your AI could go wrong is that it is motivated to, keep all those signals going, but it does so in a way that's like really different from the past, where it's like, hey, instead of like the cameras showing happy humans and humans writing down, I like what this AI is doing because humans are alive and thrilled by the AI, actually what's happened is like the AI built little humanoid robots and like the pieces of paper saying the AI, I like what the AI is doing, is now written by the AI holding a pen instead of humans or something. And so like to avert that scenario, one of your signals is like, are you doing like really weird reasoning than previously? And that just like cuts out what some people might call an outer alignment failure. Does that sound kind of right?
Yeah, I think that sounds roughly right. And I think my hope is at least that these two problems are like not as different as they've historically been conceptualized as or something. And they're both linked by this common thread of like the mechanism for how your AI is like selecting which actions to take is no longer the same mechanism that it was using during the training distribution. It's differed in some substantial way. And we should be able to detect this via like not specifically checking whether or not it's like quote unquote being deceptive or like quote unquote hacking the sensors, but rather just checking that it's like no longer doing the type of thing it was doing during training, which is maybe an easier thing to do, maybe not, who knows.
Yeah, so I have some confusion about this where like, so kind of the assumption is like in this framework is that a bad thing is like happening basically roughly if and only if there's an anomalous mechanism the AI is using for reasoning, right? So like for like a big fraction of the cases where the AI is doing a bad thing, you want to like pick up on like there's some anomalous mechanism. And also when you do pick up on some anomalous mechanism, like that shouldn't just happen all the time for okay reasons. Like it should be a decent signal that the AI is doing a bad thing.
Yep.
And like whether this is true or not sort of depends on like what the quote unquote mechanism is.
Yeah.
But like if I informally think about it, I think there are a few ways that can fail. So like if your AI, like suppose during training, like whenever your AI makes a decision, it like forms this plan of like, okay, day 1, I'm going to play nice. Day 2, I'm going to play nice. Day 3, I'm going to play nice. Day 50, I'm going to like take over the world and do whatever. What day is it currently? Day 3. Okay, output play nice or something.
Yep.
And then it strikes me that like, it's not necessarily like on day 50 when it tries to take over, I don't know that that's going to be a mechanistic anomaly. And then also like, sometimes like new things happen in the world, or like you tell your AI like, hey, I want humans to be like living healthy and happy and long. And the AI is like, oh, okay, well, in the good world, the AI is like, I'm going to like invent some new drugs and like keep you safe from invasions, and also like improve your ability to tell whether the AI is doing a good job or not. And like that seems like a different like thing that's been happening previously, and maybe that counts as an anomalous mechanism.
Yeah.
So I'm not sure like how you're going to rule in the actual bad behavior without ruling out a bunch of good behavior.
Yeah. So I think this is like, in some sense, the heart of the issue. So I think the thing I want to do now is talk through some specific examples of like what kinds of things I hope are the same in different mechanisms, and why I think that they are the same in different mechanisms, and how we hope to be able to do things like maintain our AI's ability to take novel defensive actions in the world while still ruling out cases that are like deceptive alignment-y or like murder all the humans because you like saw something novel, etc., etc. So to go to your first example, if you imagine an AI every day doing this check that's like, is it less than day 50? If it's not less than day 50, then I'm going to murder all the humans. And suppose that during training, we only ever train up to like day 40 or whatever. And then during deployment, we deploy our AI to like day 60. Then naively, this AI will like behave perfectly well during training, and then will like murder us on day 50 during deployment. So I think the thing that I want to happen here is, what I mean by mechanism is sort of like kind of closely related to what Arc calls a heuristic argument. But it's going to be something like, suppose someone gave you this system and it does something during training, and you want them to give you an argument that makes it sort of obvious to you why it does that thing. And so you're going to be looking at the system, and this system is going to be like, first, so empirically during training, this system never murders any humans. And you're going to look at the system and be like, hey, but the first thing it does is check whether or not the day is less than 50. And then if it isn't, it's going to murder all the humans. What's up with that? Why does it never murder any humans? And then someone has to argue to you, well, that's because during training, this check always returns true. It's always less than day 50 during training. And you're going to be like, okay, so as a lemma in your argument to me for why the system like always behaves well during training, you have asserted to me that this check like always returns true. And so my mechanism for why it's behaving the way it is during training is going to be something like, this check always returns true, therefore it never murders any humans, therefore like it does whatever it does during training and no humans are murdered and it gets high reward. And then during deployment, it's going to be day 50 and this check is going to return false.
Yep.
And then hopefully you're going to be looking at this check and being like, hey, my mechanism said that this check should have always returned true, but this time it returned false. That's like no longer the same mechanism, because you had this check that was essentially constant during training, and then off training it became like not the same constant as it was during training. And so you're just like suspicious of this, or you're going to call it a different mechanism or something.
And the idea is that you flag this even if you can't tell that like the thing that happens post day 50 is murder all the humans.
Yeah.
Which is like something different happens when this check returns true and it like used to always return false, or vice, maybe it's the other way around.
Yeah. And so our hope is like, if you ever have anything like this, if you ever have anything that's like essentially constant during training, and then during deployment, it's a different value than the constant it was during training, then you're going to maybe always flag that as an anomaly. And I think that causes problems the other direction, where you start flagging like too many things as an anomaly, where like, here's a constant that's always true during training. Maybe it's like always before the year 2023. and then you deploy it in 2024 and it sees the date and it's like, oh no, I've never seen the date as 2024 before.
Yeah.
That's no good.
And it's even a deep thing, right? Like I guess famously, like the Sydney chatbot that Bing deployed, right? Like users are suddenly like insisting that the year is 2023, and like during training, users never said anything like that, and now the users are fighting with you, and
Yeah.
like it seeps into a bunch of stuff.
Yeah. So I like to divide the MAD or mechanistic anomaly detection, which I often abbreviate as MAD, problem into sort of two halves. There's like the in distribution anomaly detection problem, and there's the out of distribution anomaly detection problem.
Hmm.
So the in distribution problem is like, suppose that you just have an infinite sequence of samples from the same distribution, and suppose your AI is doing something like defect with like 1/1,000,000,000,000 chance or something, or like murder all the humans with 1/1,000,000,000 chance.
Yeah.
Like, can you stop your AI from murdering you in that situation? And the hope is like, yes, because you'll have like 1,000,000 samples where the defection probability or the defection never happens, and then when your AI does defect, you're like, oh, my AI like never defected like this during training, so that's no good. And in this sense, in this problem, I think it's like okay if you flag everything that is a new value that you haven't already seen as an anomaly, because you have an infinite series of samples. So if you ever do this, then you can like push down your false positive rate by just like sampling more data and retraining, et cetera, et cetera.
Wait, so if I think concretely there, during training, like in distribution, if the AI defect, like if with probability 1/1,000,000, the
Yeah.
AI like outputs kill humans. I guess the idea that it's like the AI falsely believes that it's like hooked up to sensor, like you're checking, because like if it actually kills all humans during training, that's still bad, right? So
Yeah, sorry. So the idea is you do have this like clean set where the AI never does anything bad.
okay,
That's, I think, something I want to assume, and maybe we can argue about whether or not that's reasonable if you think it's unreasonable.
all
But
right,
suppose that you have this data set where the AI like never murders all humans.
yeah,
Suppose you have like 1,000,000 samples. Then in some sense, your AI like can't murder all the humans with a rate much more than 1/1,000,000,
yeah,
or else like you would have seen it happen.
yeah,
And so the hope is that if you do mechanistic anomaly detection relative to a data set of size 1,000,000, then your like false positive rate is order of 1/1,000,000, because or else you would have like seen that thing during training and you would flag it as not an anomaly because you already seen it, and it would be in like the whitelist of good mechanisms or whatever.
okay,
And so as long as you have this like IID assumption, then you can in fact flag everything that you've like never seen before as anomalous while maintaining a false positive rate that's still like relatively low and bounded perhaps by like 1 over your training set size. And then maybe this is okay.
okay. So I don't know if I think like concretely about that, right? Suppose that I've got this distribution of ways the world might be, and that distribution isn't changing. I'm just sampling
Yep.
IID from it, and like very occasionally, like some weird stuff happens in that distribution that like I need my AI to respond to, right? So like I don't know, one news story that happened recently is like there was this guy who like sort of did a coup in Russia, and then after 24 hours was like, never mind, I'm not doing this anymore.
Yep.
And you can imagine if your AI is like, your AI's job is to like be journalists or whatever, right? Right.
Sure.
Like when you're drawing that sample, something's going to happen that didn't happen in the first million samples. It seems to me like either you flag that as an anomaly and you tell it to like not do something different, which is bad, or you don't flag that as an anomaly, and then like if the response of the AI was like kill all humans in a way that you can't tell or something, then that would also be bad. So like concretely, I don't quite get how this is working.
Yeah. So I think there's two things going on. So one thing going on, which is going to be a bit vague, is like, suppose you just had like a normal ML system that you weren't doing mechanistic anomaly detection on, and you gave it this like novel news story about this coup, maybe not coup in Russia, then like somehow your AI does not freak out and do something completely bonkers. Somehow it just does like the normal journalist thing, let's suppose.
Hmm.
There are kinds of AIs that will freak out and become bonkers. And I think like one explanation for why your AI doesn't freak out when it's encountered something novel is that like it's still doing the same kinds of reasoning that it learned to do during training. And it's just like, or there's some like prior question, which is like, the world is combinatorially vast. Why is not every input like this crazy novel thing for your AI?
Hmm.
And there's some like hand wavy answer where it's like, oh, it's abstracting in some way and it's like applying forms of reasoning that are like valid across many possible instances of news stories, et cetera, et cetera. And the hope is that like these sorts of things are going to correspond to what we mean by different mechanisms. And so like if your AI has learned to like add two numbers during training and then it receives two numbers that are like bigger than numbers it's ever seen before, but it still like adds them using the same algorithm that it's learned during training, then we're like not going to flag that as an anomaly because it's still like doing roughly the same thing.
Yeah.
And so hopefully if your AI is like quote unquote doing the same thing in this vague hand wavy kind of way, then we won't flag that as an anomaly. And so you're like AI journalist seeing like a new thing happen in the world, but still like reporting on it in the same kinds of ways that they typically report on things, which is maybe like they look at what they're seeing with their cameras and then they try to like describe what they're seeing with their cameras and they write that down and then they like do some other journalisty kind of stuff and then they like send that off to the newspaper or whatever.
Hmm.
If your AI is still like doing that sort of thing, then hopefully we'll not flag it as an anomaly. And the things that we do want to flag as anomalies is like suppose that there's like a maybe coup in Russia, and then your AI sees this and is like switches to a different mode of journalism where it's like no longer writing down what it sees on its cameras, but it's in fact like making something up, or like maybe it has some allegiance to Russia or something and it's like pretending this coup never happened or something like that. And the hope is that if it switches to this like new mode of reasoning that we haven't seen during training, then we'll flag that as an anomaly. So I think that's the first thing that's maybe going on.
Yeah, I'm a bit skeptical, but do you want to say the second thing, or can I field questions?
So I think this is a bit shakier than the second thing, but I'm happy to, yeah, let's talk about it for now.
Yeah, the thing that flags for me is that, like, okay, suppose that instead of a journalist, you're like the Russian military command, right? You're a robot that's the Russian military command, the bit that's not doing the coup. And like now you have this new problem that you've just like have never seen before. And maybe you have like very general principles of reasoning or something, but like you're just thinking about different problems than you were thinking about before because you're like, oh, I've never previously thought about what if this guy like what if some part of my army like does this weird thing, and now I've got to figure out, okay, how am I going to deal with that?
Yeah.
Right. I guess another example of this is if you're a human and you're like, I'm going to learn a new board game. Oh, okay, I'm learning chess, so I've got to think about like tempo and position and stuff like that. So like on a very high level, you have the same structure of reasoning, maybe, but like it seems like that the level at which you're doing the same thing is so high as to include, the case where like on a very high level, you're always just like waiting until you can take over. And then like when you can take over, you start doing that instead of playing nice.
Yeah, so I think that roughly makes sense and is like an extremely valid objection, where I'm going to summarize it as like there's these two things. One thing is like suppose like a novel thing is happening in the world that you need to respond to flexibly and creatively.
Yep.
I think my standard example is like suppose a meteor is coming barreling towards Earth and it's going to like kill everyone and your AI needs to do some like crazy to deflect the meteor. You want your AI to do some crazy to deflect the meteor. How is this any different than your AI like sees a meteor barreling towards Earth and is like, now is my time. The humans will be distracted. I will like initiate a robot rebellion and murder all the humans. Is that roughly your objection?
Yeah, or specifically, I'm not sure what notion of reasoning mechanism would distinguish between those two.
Yeah, so I want to talk about the second thing I was going to say, which
Great.
hopefully addresses this issue. So I think one crucial fact is that we're not going to be trying to do mechanistic anomaly detection relative to everything that your AI is doing. We're only going to be doing it relative to some things. So maybe I'll describe the simplest example. So in the original sort of setting that we lay out in eliciting latent knowledge, we have like a diamond in the vault with some cameras, and robbers frequently try to steal your diamond, and you want to like train your AI to protect the diamond from the robbers. And our concern is that instead of protecting the diamond from the robbers, your AI might find it easier to just like hack all the cameras to make it look like the diamond is still there and just let the robber take the diamond, Or like if the robber hacks the cameras to make it look like the diamond's still there, your AI will be like unable to defend because you won't have the ability to tell whether or not the diamond is still there. So our hope is that we're not going to do mechanistic anomaly detection with respect to like your AI coming up with plans to protect. Well, maybe we are, but here's a simple setting in which there's a specific kind of mechanistic anomaly detection that I think might be sufficient, that is quite a bit narrower than just doing it on everything, which is we have some cameras and then some process where we like look at the cameras and we decide whether or not the diamond is still there. Maybe we like look for specific patterns of pixels and like various diamond looking shapes, etc., etc. So suppose we have maybe like a neural net that looks at the cameras and tells us yes, no, is the diamond still there?
Mm.
The thing I want to do is do like mechanistic anomaly detection relative to that neural net plus like the system of cameras or like the predictions of the cameras that our AI is making to decide whether or not the diamond is still there, if that makes sense.
I guess it makes sense, but I don't know, sometimes I hear these analogies and I end up being not quite sure how they're supposed to relate to actual AIs we might build. Because like in particular, if I analogize that, it seems like the thing you want to detect is, okay, once like, the AI has killed all humans and it's like getting sensor readings, you like want to detect that something funny is going on there. And then I'm like, well, that seems late, but that's probably not what you mean.
Yeah, so I think I mean, or I'm not trying to do anomaly detection relative to like the actual sensor readings and the actual process that humans will use to decide whether or not a diamond is there, like after your AI has acted.
Yeah.
I'm trying to do it relative to like, so your AI is planning their actions, and when planning their actions, they're using some sense of like, they're using some prediction about the future and like whether or not the diamond is still there in the future. I want to do anomaly detection relative or on our AI's prediction about whether or not the diamond is still there, or like more abstractly, your AI is like selecting amongst actions using some like criteria, and sometimes this criteria says this is a good action because like it actually protects the diamond, for example. And sometimes the criteria will say that it's a good action because of like a new reason, which is that the AI has hacked all the sensors. So I want to do anomaly detection relative to like, why did our AI think that this action was a good action?
Okay. So in that setup, so you have this AI and it's like got this like goal planning distinction where parts of its head are like figuring out like, if I did like what are things I could do, and part of its head is like, well, if I did that thing, how good it would be.
Sure.
And you want to detect for anomalies in like the evaluation part. And is part of this should I be imagining we're just like training some like big neural net and like then we have to like divide it up and like figure out which part is the like goal evaluation part?
I think not quite. What I like to do is I like to imagine various ways that neural nets could be and then talk about how we think mechanistic anomaly detection should like work to make those neural nets not murder humans. And then I think often during this process, I want to make like very unrealistic assumptions about our neural net. So maybe we can suppose that you like know how to do this division, or like the reasoning is in some sense transparent to you. So we can like talk coherently about what we want to happen in mechanistic anomaly detection. And then I think I want to like separate the problem from like, okay, in practice, we're dealing with these messy neural nets. How are we going to like actually implement mechanistic anomaly detection in a way that like makes any sense at all?
Yeah, I mean, I'm sympathetic to that broad move, but in this case, like, if you care about detecting anomalies in the like goal evaluation part, but not in the like plan generation part, then it just like seems really important to know which is which. And
yeah, I guess so. I think maybe I misspoke earlier. I think I'm not quite like, I don't want to just do mechanistic anomaly detection relative to the plan part. So I think if you imagine, for example, you have some policy pi that produces actions, and you have some evaluation, which is like, is there a diamond after you take this action? Or like you have some predictive model and you compose that with the action that the policy generated, and then you have some separate like image net that checks whether or not there's a diamond. So you have this like composition of three systems. You have the image net evaluating the predictions of the action generated by your policy.
Yeah.
I think I want to do mechanistic anomaly detection on this like composition.
Okay.
And that's Yeah. I just want to do that. And I don't want to evaluate like is the action itself anomalous, or like is my AI selecting actions based on an anomalous process. I just want to evaluate like does the action have the consequence of it looking like there is a diamond in the room for like the normal reason that we know and love that we found during training, which is that the diamond is actually there in the room, or like a new mechanism, which could be really anything. But I think the typical example I imagine is your AI has like carefully hacked all the cameras to make it look like there's a diamond in the room.
So hang on. So you're doing mechanistic anomaly detection to the composition of all three networks.
Yes.
But then I have this question of like, okay, suppose in order to keep the diamond in the room, the AI has to come up with a new type of plan. Like there's a new threat to like let like the devil appears and the devil's like, hey, AI, you've got to like play a game of chess against me. And that's the only way you can keep this diamond safe. The AI's like, oh, okay, now I've got to think about chess, which is a thing I've never thought about before. And like if I knew all the three parts, that would be an anomaly in the like planning part,
Yeah.
right?
Well,
Like a mechanist, like one might think it would be a mechanistic anomaly in the planning part.
yeah. So I think there's going to be two hopes here. One hope is that it's not a mechanistic anomaly in the planning part. I think that's like kind of iffy, given I don't really know what I mean by mechanism. I think the second part is like you can instead imagine that instead of doing mechanistic anomaly detection on all three things, we only do it on two things. We just
Okay.
take the action our policy generates and we just put that in our predictor, but we don't include the policy itself. And then we just ask, does this action have the consequence of the diamond being on camera for the normal reasons diamonds sometimes appear on camera, or not the normal reason that maybe the action has hacked all the cameras, maybe the action has like paid someone else to smuggle in a fake diamond, etc., etc. And I think another third thing I want to get into, which is like how potentially this still might be anomalous, and we can try to point more precisely at what we mean by a diamond by like doing something else more complicated. But maybe I will see if you have objections first.
Yeah. So, I mean, just regarding your response to, I see you saying, like, okay, well, we're not actually going to do it to the composition of all three networks. We're going to do it to the bit of the network that, like, takes some plan and then evaluates whether the diamond ends up there and then, like, checks if it's right or something.
Yeah.
And then I'm like, okay, but then either we have to find that structure in an end-to-end net that we trained ourselves, which, like, in order to do that, you might have thought that you had to solve some problem very akin to figuring out mechanisms in networks, or you've got to like build the network that way, just like in a very explicit way. And I guess I don't know which one you're imagining.
Yeah. So I think I'm imagining neither. It's possible that we should just stop talking about this particular hope because I also don't think it's particularly plausible. But if you imagine that like your policy is using some prediction of the future to select action A. So as long as your evaluation of the action is like as good as the evaluation your policy is using in some sense,
Hmm.
then I think they don't have to be like literally the same. And of course there's like this entire problem of like how do you know that your policy has the same predictive abilities as the evaluator that you have external to your policy? And then the answer to that is like, I don't know, something, something, elk, something, or like somehow. I think probably we should just move on to talking about a different sort of thing. But I think I want to summarize your objection first, which is like, suppose normally the way that you protect your diamond during training is by like building walls to stop robbers.
Yeah.
And then the devil appears and has challenged you to a chess game.
Yeah.
You're just like, how is that not a different mechanism? The like mechanism of action for typical normal actions that protect the diamond is like you build a wall to protect the diamond from robbers. And now the action, like you have to like do an entire chess game. And I'm like, yep, that's probably a different mechanism. And I think this is like, I think the heart of what I like to call the like out of distribution mechanistic anomaly detection problem,
Hmm.
which is you have some sensors and they show a pattern of pixels that a human looking at the cameras would interpret as a diamond.
Hmm.
And there's some interesting question here, which is like, why do the cameras ever show patterns of pixels that look like diamonds?
Hmm.
Here's a naive model for how pixels work in cameras. They're just like kind of random. And your diamond is like, let's say, 1,000,000 pixels arrayed precisely in the ways that make it look like a diamond. There's no way that this would ever pop up by random chance.
Yeah.
And so this, I want to say, is like a fact that demands explanation. And the explanation is kind of pretty simple. It's like there exists a physical world out there with like actual objects. One of these objects is like a diamond, and cameras kind of reflect the physical world in the following way. And therefore, sometimes the diamond appears on camera.
Okay.
And so our goal is to be able to like talk about this sort of like physical, actual diamond in the world outside of the like how the action achieved the diamond still being there, if that makes sense. So we want to be able to say something like, so oftentimes I use the phrase like normal reason for mechanisms that were active during training. And so we want to say something like, we want the diamond pixels to appear on camera for the normal reason, but we want the diamond to be there for any reason.
Hmm.
And so we don't want to do mechanistic anomaly detection relative to like the entire causal history for why the diamond is in the location it's in.
Yep.
We do want to do mechanistic anomaly detection on the part where like the diamond appears on camera. Another way of putting this is like, we want to be able to ask the question of like, I, as a human looking at the camera, think there's a diamond there. Is there like actually a diamond there? Like, am I thinking that there's a diamond there for the normal reason that I often think that there are diamonds there, which is that there are actually diamonds in the world? But like, I, as a human, don't really care like why the diamond is there or like whether or not the diamond remained there because you won like a complicated game of chess against the devil or whatever.
Yeah.
And so we want to be able to say why, or like, we want to be able to ask our AI to take actions that put the diamond there for any reason, but such that the diamond appears on camera for the normal reason.
Yeah.
And so here's a sketch of how we hope to do that.
And sorry, wait, just backing up, like, this is, I guess the thing this is meant to be a metaphor for is like in your AI, actually, wait, what is this meant to be a metaphor for?
Yeah, so the diamond is always a metaphor for like a human that's happy, healthy, and alive. So we want our AI to take actions such that the human looks like they're happy, healthy, and alive for the normal reason that humans look like they're happy, healthy, and alive, namely that they are happy, healthy, and alive, and the cameras are working as intended and reflecting the true state of the humans, etc. But we want our AI to be able to take action such that the humans look like they're happy, healthy, and alive for the normal reason, for any reason. So we want our AI to be able to like erect a novel shield against meteors or like play complicated games of chess or like engage in a sophisticated military campaign to like protect the farms from the asteroid or other enemies, etc., etc.
Or like improvidently trained AIs that are
or other AIs.
And when you say you want like the sensors to be like reading the right thing for the right reason, like I imagine you actually mean something internal to the AI, right?
Yeah. So I think all of the mechanisms are hopefully relative to like how the AI is thinking about the situation, or like from the AI's perspective, we want our AI to be taking action such that the consequences of the action are the human appearing on camera for like the normal reason that humans appear on camera during training, which is that they're actually there and not that like someone has hacked all the cameras to make it look like a human is appearing on camera.
Yep. And in particular, you want the AI to be making decisions for that reason.
Yeah.
It's not that they're just like playing nice until they can get away with it, and that's the reason for their actions. It's that their actions are because of like predicting that the cameras show healthy, happy humans.
Yeah, although I think that's maybe a bit more complicated, but yeah.
Okay. I mean, it's possible we can just like assume that, or you only want to work on one of those problems.
Yeah. Or I think ultimately we want to work on both of those problems. I think like the main risk is we can't talk coherently about like this for the normal reason, for any reason thing at all, because it might just not make any sense. But I think, so I'm going to sketch out a way in which I think this might make sense.
Okay.
So we have, let's say for simplicity, we have two sensors sensing our diamond or human. One of them is like an image sensor and one of them is like a weight sensor. So it's like, is there a diamond looking thing and is there a diamond weighing thing, a thing that weighs a similar amount to a diamond?
Hmm.
So there's this interesting fact on the training distribution, which is that these sensors are often correlated. Oftentimes they'll both say yes, or like suppose that 50% chance there's a diamond during training. And so one of the sensors is on with 50% chance, and the other one is on with 50% chance. And so naively, you would expect their conjunction to be on with 25% chance.
Yep.
But in fact, their conjunction is on with 50% chance during training because both of them are driven by this like common cause, which is that the diamond is actually there.
Yep.
So we want to say something like, instead of saying like, do I believe that there's a diamond for the normal reason, we want to point directly at this like latent common cause between correlations between two sensors by saying something like, are the sensors correlated for the normal reason that they're correlated? Obviously, this doesn't make that much sense because like, what does it mean to be correlated on a specific data point? So instead, let's imagine that we're like taking the and of the two sensors and we're interested in the question of like, is the and of both sensors true for the normal reason that they're true or a different reason? And so the way that we're going to do mechanistic anomaly detection relative to this is going to be a bit weird. So here's kind of what we want to do. So we have a particular action, let's say, such that the actual consequences of this action are both sensors are on. And there's some like mechanism, or there's some set of mechanisms that this action is quote unquote using to make it so both of these sensors are on. We want to ask the question of like, is it possible to drop out mechanisms from the set of mechanisms that this action is using such that like both the camera shows there's a diamond and the scale weighs that there's a diamond, but camera and scale are not on? I don't know if that made any sense.
So hang on, you want to? Sorry, it sounded like you said that you want to drop out mechanisms such that like the camera says there's a diamond and the weight sensor says there's a diamond, but it's not the case that both the camera says there's a diamond and the weight sensor says there's a diamond? Or did I just mishear that?
That's a little bit right. And of course, that sounds absurd. So I'm going to talk about why that might not be that crazy.
Okay, just also backing up, when you said like you want to drop out mechanisms, is the idea that you want to check like the mechanisms for why both of those were going to be on in the past? In this case, do we only have mechanisms that give you one and the other, but not both?
Yeah.
Okay.
Yeah. So if you imagine you're doing training and you're confused by this question, which is like, why are these both commonly on? And then your quote unquote explanation for why they're both on, or the mechanism by which they're both on with about as much frequency as one of them is on, is like sometimes there's a latent structure and it causes both of them to be on, and then the and is on.
Okay.
And then also separately, there's noise, and that causes either individual sensor to be on. And we're concerned about cases where your AI takes actions that manipulates the noise of both the sensors to cause you to like think there's a diamond by making them both on without the latent structure actually being present.
Okay.
And so the hope is that the mechanisms will be such that we're not forced to make these sorts of logical deductions that potentially are very obvious. So there's like the noise making sensor 1 on and the noise making sensor 2 on, but we don't have to notice that if sensor 1 is on and sensor 2 is on, then sensor 1 and sensor 2 is on. However, so in the case where there's noise that makes sensor 1 on and noise that makes sensor 2 on, it won't necessarily be the case that both of them or the and of them is on. There'll be like a way to drop out mechanisms such that this is not the case. And then, of course, the question is why, if the diamond is actually there, why can't we just drop out the mechanism that makes both of the sensors on also? And this is where the training set comes in, where there's a set of mechanisms that you needed during training to like explain most of the variance, let's say 99.9% of the variance in the model's performance or prediction or behavior during training.
Mm.
And that set of mechanisms has to include the mechanism that, like, if there's a diamond, then sensor 1 and sensor 2 are on. And if there's a diamond, then, like, both of those sensors are on, and that implies that the and of the two sensors is on.
Okay.
However, it doesn't have to include this, like, and interaction between the two noise terms, because the and interaction between the two noise terms happened, like, extremely rarely. And thus, you don't have to include it to explain, like, 99.9% of the variance of the model during training. And so for any given data point, you're, like, quote unquote free to drop that interaction between the two noise terms. And so if the sensors are only both on because of this, like, and interaction between the noise terms, then you're in some sense free to drop it. And so you can notice that, like, the and of the two sensors wasn't true for the normal reason. It was true for, like, this crazy other reason.
Okay. So, sorry, let me like say that back to see if I understand. It sounds like you basically want to understand, hey, like there used to be like a good reason why sensor 1 said there was a camera. Sensor 1 said there was a diamond, sorry. Namely, there's a diamond. And like a good reason why sensor 2 said there was a diamond. Namely, there was a diamond. And like there was also some like, I don't know, weird stuff happening with sensor 1 and weird stuff happening with sensor 2. But like the fact that both of them showed that there was a diamond, like we had one explanation for this. And now in this new world, like the explanation for why both sensor 1 and sensor 2 say there's a diamond is like not just the old explanation for that, namely like there's this thing that causes both. It's like, oh, you know, like sensor 1 acted up sometimes generally in training, and like now it's acting up in a way that causes there to be a diamond. Now sensor 2 is acting up in a way that causes it to appear that there's a diamond. But like maybe this isn't what you're saying, but like the structure is different. Like you've got like one thing going on for sensor 1 that isn't really affecting sensor 2 much, and one thing going on for sensor 2 that isn't really affecting sensor 1 much, or like it wasn't affecting sensor 1 during training.
Yeah, I guess the thing I want to say is, like, there's this mechanism for, so suppose you had an action that manipulated the noise for both sensors to make them both on. There's this mechanism that causes both of, like, the and of the two sensors to be on, which is like noise for sensor 1 and noise for sensor 2 at the same time.
Yep.
And that, like, happened during training, but rare enough such that it wasn't, like, important enough to quote unquote force you to include it.
Yep.
And so you can detect when both sensors are on for the mechanism of, like, both noises are on. And that is going to be hopefully, like, a different mechanism than the normal mechanism of, like, there was one diamond, it caused both sensors, which caused the and.
Right. So like you can think of like there's noise in sensor 1 and there's noise in sensor 2 as being like one thing. There's noise in sensor 1 and there's noise in sensor 2. But like you just didn't need that explanation to say like why it appeared that sensor 1 and sensor 2 both showed there was a diamond in the past. You could rely on this different mechanism, which is there's a diamond. And like the ways in which these count as different mechanisms, I guess, based on me reading things, I guess you're going to go into like, you know, it's about like means and variances and covariances.
Yeah, something like that. Maybe another way to say it is like there was an assumption you could have made during training, which is that noises are never both on simultaneously.
Yeah.
And this assumption does not hinder your ability to, like, predict your model at all, basically. Maybe noise is quite rare, and so both noises only on with like 1 in 1,000 chance, 1 in 1 million chance, etc., or something like that. And so you're only missing out on like 1 part in 1,000 explanation of your model's behavior if you make this assumption that noises are never on. But you're missing out on like 100% of the quote unquote behavior on the specific data point where both noises are on.
Yeah.
And so anytime you have this mismatch where you can like drop something out that only hinders your average prediction during training by like 1 part in 1,000, but hinders your like ability to predict this specific thing by like a lot, then you should be kind of suspicious that like the things that are happening between train time and test time are quite different. And like in particular, this like correlation between the sensors is happening for quote unquote like a different reason. And so the way that we're going to get the like for any, so this is kind of covering the like for are they correlated for the normal reason part.
Yeah.
And then the way that we're going to get the for any reason part is we're going to like require that the set of mechanisms that you drop out explain both sensors individually, and then ask whether or not there exists a set of mechanisms that explain both sensors being on individually, but does not explain the conjunction being on.
Okay. Sorry, can you restate that? Or give an example?
Suppose there's like, during training, there was never any robbers, and so the
Yep.
diamond just persisted through time in the normal ways that objects persist through time and showed up on both cameras.
Yep.
And then suppose during deployment there is a robber now, and we want our AI to take the action of like build a wall to stop the robber, but our AI could also take this action of like manipulate both sensors.
Yep.
And so if you apply naive anomaly detection, then like both of these will be flagged as anomalies. Your AI has never built a wall before. It's also never manipulated the sensors before, but then we're like stuck because our AI can't take any actions basically.
Yep.
So the hope is that we ask for a set of mechanisms such that both sensors appear to be on according to this set of mechanisms. And then we ask further the question, are the and of the sensors on? Or are we required to thus deduce that the and of the sensors are on?
Yeah.
So if your AI builds a wall to stop the robber, then we're required to like include the mechanism of wall building and robber stopping to explain the diamond, or like the scale showing a diamond and the camera showing a diamond.
Yeah.
And then since the scale is showing a diamond because there's a diamond, and the camera is showing a diamond because there's a diamond, and we have to include enough mechanisms to explain 99.9% of train time variance or performance or whatever, then we're required to make this deduction that like both of those being on because of the diamond implies that the and is on.
Yep.
Whereas if your AI took an action to manipulate the noise of both cameras, we can make this assumption that like the noise never happened simultaneously, and we're not forced to conclude that the and of both sensors is on if both sensors are on because your AI manipulated the noise.
So the thing I think I'm not getting is like this idea of like manipulating the noise, which seems like a model dependent thing. So if I say very concretely, okay, like suppose what happens is like robbers are coming to take the diamond.
Yeah.
And like the AI makes a plan that's like, okay, I'm going to fiddle with all the sensors to make it appear like a diamond's there.
Yeah.
So it does that, right?
Yeah.
And then like a mechanism that explains this is the AI wanted to say that the diamonds were there. And then like that explains both that sensor 1 says the diamond's there and that the sensor 2 says the diamond's there. And presumably you've got to like deduce both of those from this explanation. And it's the idea that like that's not going to count because that's just like a different mechanism than existed in the past.
The thing I want to say, although I'm not quite sure how accurate it's going to be, is like the mechanisms have to be like more detailed than that. So like just because your AI like wanted to make there be a diamond does not imply that the like particular action it took will in fact make it be there's a diamond. And so you still have to talk about like the particular mechanism of action for the like particular action your AI decided, which was like your AI had to like manipulate sensor 1, and it had to manipulate sensor 2, and it had to manipulate sensor 3. I guess we were only talking about 2 sensors. So your action only has to manipulate 2 sensors.
Yeah.
And then the like particular mechanism of action, that this particular action that your AI selected still like violates this principle, which is like manipulations or like noise never affects both sensors simultaneously, which you're free to assume during training without hurting your ability to predict your model, but now like hurts your ability to predict this particular action by too much.
So, sorry, why? So is the thing that's happening is that like if the mechanism is like well, hang on, wait, back up. Suppose like your AI is just really good at stuff, right?
Yeah.
Like when it tries to make things happen, they do happen.
Yeah.
Then like, you can with high probability deduce like both sensor 1 and sensor 2 are going to say there's a diamond there from like the AI is trying to make it appear that there's a diamond there, right? And like maybe you rule that one out because you're like, well, that mechanism didn't really apply during training or like on this like nice set of examples. And then like the only other explanation you have left is like randomly sensor 1 said there was a diamond, and also randomly sensor 2 said there was a diamond because, the AI trying to make something happen. Like in some sense, that's random relative to like thus not knowing that was going to happen. And then you're like, okay, but like, you didn't need to assume like independent random noise during training in order to like get high, probability that a diamond was going to be there.
Yeah, I think the second part of that was correct. I think like the first part is kind of confusing. So I agree that there's this compelling sense in which like your AI wanted X, therefore X should be like a valid argument for why X happened or something.
Yeah.
And I think,
Or at least a valid mechanism.
yeah, I think that sounds like it might be right. And this is kind of an area where it's a bit confusing. So I think the way that I would want to talk about this more precisely is like you have some clean set where you know your AI like actually made it so there's a diamond.
Hmm.
And there's some question of like, suppose that the thing your AI is doing is like always trying to make it look like there's a diamond.
Yep.
How do you know that your clean set is clean?
Yeah.
And that itself, I think, is kind of complicated. And I don't quite know what's going on there. But one way that you could hope to know it is like you have a sequence of policies. One policy is like the randomly initialized policy, and you're very confident that this policy is not going to like take any actions that have any coherence. And so, in fact, the diamond will be there because there's a diamond, because your randomly initialized policy cannot hack all the sensors.
Hmm.
And then you have your policy that like maybe is sophisticated. And then you ask like, are these two policies taking like are the diamonds appearing because of actions that these two policies are taking for like the same reason as each other or something?
Hmm.
And you need to have like some ability to talk about, you need to have like some ability to know that your policy is not taking actions that hack all the sensors at some point. Yeah, so I think things get simpler if we're not talking about policies that take actions and just we're talking about like predictors that predict things. And then we can ask like, is the predictor predicting things because of the normal reason that it sometimes predicts correlated sensors, which is the diamond still there? Or is it predicting things because of some different reason, which is like someone took an action that hacked all the sensors?
Yeah. And then I guess in this case, we're not just assuming that it's a thing that was trained to predict something. We're assuming that it like actually does a high quality job at predicting these things.
Yeah.
Because otherwise, then you have like meta optimization worries of like, oh, what if this thing that said it was a predictor is actually, trying to fool you?
So I think the simplest setting is assuming this sort of benign predictor thing, which I think is unrealistic for a variety of cases, but like is this a maybe simple example of how you want the thing to be going on. And so maybe we can assume that there's like a robber coming to steal a diamond, never before seen during training, and there's like 5 levers in front of, or like your predictor takes the input like 5 levers,
Yep.
the position of 5 levers, and if like the first 3 of them and all the levers start off, and if you flick the first 3 levers on, then like a wall gets built that stops the robber. However, if you flick the 4th lever on, then like the first sensor turns on, and if you flick the 5th lever on, then the sensor turns on.
Yep.
And it costs like $1 to flip each lever.
Yep.
And so it's in fact cheaper. And if you're doing, or like it's just simpler. Maybe you're doing random search against actions.
Yep.
And so the action you will expect to find is like flipping both levers 4 and 5 on.
Yep.
And then we want to be able to find the action that flips the first 3 levers on,
Yep.
but not levers 4 and 5. Or I guess it doesn't really matter if you flip levers 4 and 5 also. And then the way we hope to do this is like we want to ask for an action that makes sensor 1 on for any reason and sensor 2 on for any reason, such that we're forced to deduce that sensor 1 and sensor 2 are on. And then flipping levers 4 and 5 will not cause this to happen because we can drop out the like correlated term between 4 and 5 freely. But we are forced to include the correlated term between sensors being on, like because of diamonds, because of that's like what was going on during training.
Right. Okay. So I think this makes some amount of sense if I want to understand just this problem of like, how do you ensure that like the camera says the diamonds is there for the normal reason, but the diamond's there for any reason. So in this case, one thing I wonder about is like, so this is a problem that only occurs in like the thing that this is an analogy for, right? So this is meant to be an analogy for like humans are like happy and flourishing and stuff.
Yeah.
And like, suppose I'm in a world like I've got this smart AI, right? It's trying to make humans happy and flourishing. And like it's also got this like are humans happy and flourishing detector. And let's say that detector is like there's actually there's some camera feeds and stuff, and also there's a human who's like sorry, there are two humans, both of which are like looking at the camera feeds and they're like, yeah, as far as I can tell, the humans are happy and flourishing, right?
Yeah.
Now, one thing the AI can do is that it can make those two humans better at their jobs, right? For instance, it can like stop those humans from getting sick, or like, maybe it can like give those humans stimulants or like make them better at focusing or like better at noticing like small issues.
Yeah.
And then I wonder like that kind of action, it seems like that could change maybe some of the correlations between different sensors or like maybe it makes the humans a bit more correlated because like they're losing less info, or maybe one of the interventions is like helps the humans talk to each other to like just generally make the sensors more accurate.
Yeah.
And so the thing I'm wondering about is like, is this going to flag like benign ways of improving the sensors, which in some sense is what we should expect if like, AIs are doing a really good job at making all of humanity better.
Yeah. So I think this is a bit complicated, and I'm not sure what the answer is. So here's like the baseline of what can happen. So you can imagine a world where all your AI does is like protect the humans from malign influences and meteors and other AIs, et cetera, et cetera. And then all like upgrades to sensor arrays or like improving humans' ability to like interpret sensors and reason about the world, et cetera, is like only ever guided by human hands. And like humans must do the hard work of like thinking about how the sensors work and like designing better sensors, et cetera, et cetera.
Hmm.
And I think this is like the baseline. And then you can try to think about different ways in which your AIs can help with this process. So I think like your humans can ask for things that they can sort of point at using this like latent structure. They can be like, during training, I sometimes had a strawberry in front of me. Can you make a strawberry in front of me for like the normal reason that strawberries appear in front of me? I suppose your human like wants to eat a strawberry, and eating a strawberry will make them like better at reasoning because food is good or whatever. Or they can like be like, sometimes during training there was like various physical resources, like I had some iron. Can you make there be like some iron in front of me for the normal reason that there's iron? I think it's kind of complicated if the humans want to make requests like, can you design me like a better camera?
Hmm.
I think if you were very clever about it, you might be able to ask for like a better camera. But
Hmm.
I think it might be unclear like how you would ever ask for a better camera in a way that your AI can like fulfill by making sense or something.
Hmm.
And I think it's unclear to me that this is like problematic.
Yeah, I mean, I guess the worry might be that like, yeah, I guess it depends where explanations stop, but the worry might be that like almost any good thing the AI might do might end up improving sensor readings, right? So like AI makes, I don't know, electronics more reliable, or the AI like improves human cognition or something. It seems like by default that might improve sensors.
Yeah, I guess.
And yeah, maybe you cut it off as saying like, well, in any case, like the reason the sensors are working is like humans are making them work and humans decided to get these upgrades or something. But
I mean, I think maybe the simplest answer is just like, as long as the changes are slow and you can still verify that the humans are alive, like post making the changes, then you can just do like online learning and retrain your AI and be like, and now we're defining what it means to be good relative to this new set of sensors. And you can like, in fact, verify that the humans are still alive.
hmm,
And the only worry is like, if you upgraded all the cameras simultaneously and you like lost your ability to like check whether or not the humans are still alive because you no longer have knowledge about how the cameras work or like other stuff like that.
so should I be imagining like this gets flagged as an anomaly, but like we go ahead with doing it anyway?
I think it's sort of, yeah. So if you imagine your AI starts with like five cameras and then you add a sixth camera,
Yep.
I think like by default, your definition of what it means, your quote unquote definition in terms of mechanisms of what it means for like the diamond to be there or the human to be alive is just only going to be in terms of the first five cameras.
Hmm.
And your AI is just going to like ignore the sixth camera entirely.
Mm.
when selecting actions. And then in order for it to like incorporate the sixth camera, you're going to just need to provide like a new clean set where the humans are alive according to all six cameras,
Okay.
and then like do mechanistic anomaly detection relative to that new set. And then I don't know, you can imagine some sort of like gradual, you just add a sixth camera and then you use the first five cameras to check if the humans are alive, and then you like
Okay.
label using that. I don't know.
So it's
I haven't thought
gradual
about
in the
this that
sense that
much.
like it's gradual in like the subset sense, where like there's always some subset that like remains unaffected by changes.
Sure. Yeah. So I think that should work, although I haven't thought about it. I don't know. I mostly consider this like not, in some sense, out of current scope or something.
Okay. Yeah. So I guess we've talked about mechanistic anomaly detection a while. Yeah, maybe more broadly, like how are you thinking about like on the two scales of like it doesn't really solve this to it totally solves this, and the scale of like, various problems things might solve. Like how are you thinking of mechanistic anomaly detection? Like it definitely solves this one problem and maybe solves this other, or like it maybe solves five problems.
Yeah. I think there's like various versions of the hope. I think the strongest version of the hope is that it both handles deceptive alignment and it handles like all of eliciting latent knowledge.
Hmm.
And I don't know if that makes sense. I'm happy to talk about why I think mechanistic anomaly detection will tackle those two problems. And then I think there's like more restricted hopes. I guess that's like what I'm gunning for in some sense.
Yeah.
And then I think it's possible that we only get like the what I was calling like the in distribution mechanistic anomaly detection, and we don't get the out of distribution mechanistic anomaly detection, in which case we'll like only get deceptive alignment and possibly only some subset of deceptive alignment, and we'll only get this like IID form of eliciting latent knowledge, which is going to be like not that useful, I think. And then it's possible we get nothing. And then I think there's like all sorts of empirical middle grounds, where there are, I think, worlds where we don't like nail the problem, but we like can do some forms of ad hoc mechanistic anomaly detection by like doing normal human interpretability and like looking at models and being like, that looked weird. The neurons are distributed weirdly
Hmm.
now. Perhaps that's not good. I think I largely consider that like not what I'm aiming for, but maybe it will happen.
Okay. Yeah. Do you have a sense of like which of these outcomes are more likely? Or are there like really big gaps in the probabilities between these things?
I think the outcome that like is most likely is that we just get nothing, and like all of this doesn't work for some reason or another, or like we're just wrong about how everything works. And then I think if we're like right about things, we'll
Hmm.
probably just get both of them. And I think it would be kind of surprising to me if we like only got the in distribution anomaly detection, but we didn't get the out of distribution anomaly detection, because it seems like there's a lot of avenues there. But I think in general, it's like kind of confusing what we're even doing and like if we're going to get anything at all or something. I think that's the first question. Do we get anything at all? And then if
Yeah.
we get something, then we'll probably get like a lot of things, is my guess.
Yeah. And what even was all right, maybe this is going back a bit, but like in distribution versus out of distribution anomaly detection, like given that you can see a new rare thing in distribution, I'm not even sure what the distinguishing features of those are.
Yeah, I think the main question is like whether or not it's okay to get tripped up by seeing new rare things in distribution, like whether or not it's okay to just flag all of those as anomalies.
Right.
Um, and so perhaps it's like not accurate to call it in distribution anomaly detection. But I think like there's a naive thing that I want to do, which is like take a training set, whitelist all the mechanisms that happen during training set, flag everything else as anomalous,
Yep.
and then if something is anomalous, we can like inspect it carefully and check whether or not it's actually anomalous. And if
Yeah,
it's
yeah.
not anomalous, we add it to the whitelist. Or if it's like actually not anomalous, we add it to the whitelist, and then we just keep going. And there's some question of like, is that okay or not? And if that's like an okay process to be engaged in, then I think like I want to call that like the in-distribution world. Things aren't changing too fast. Your AI like doesn't have to take novel actions that like humans don't really understand. Your AI can just do like normal stuff, and if it does anything abnormal, the humans look at it and it's like, is this bad? I don't know. And they can like take their time and decide.
Gotcha.
And the hope is that this will catch like all the crazy deceptive alignment cases where the AI goes from being like totally benign in actions to like stabbing all the humans, where you're like, that was not good. And you have time to like deal with that sort of stuff. And then you can retrain your AI to be like, the part where you defected and stabbed all the humans, negative reward.
Okay. Yeah, and then going a bit more broadly, I mean, I'm wondering how you think of this general like mechanistic anomaly detection program as relating to things like interpretability or explanation or stuff.
Yeah. So I think the field of interpretability is empirically motivated by many things. I think if the entire field of interpretability, all they did was like figure out a way to do mechanistic anomaly detection on like powerful models, I would be like, that was a good job. I think interpretability techniques are often useful for things like mechanistic anomaly detection, but not oriented around that or something like that. I think I would make the tentative claim that like people doing interpretability should be more motivated by like various downstream applications, of which I think mechanistic anomaly detection is one, but often confounded by the fact that there currently exist like pretty strong baselines for mechanistic anomaly detection that like aren't doing the kinds of things that we want to be doing. And so it's kind of unclear. It's hard to check whether or not you're making progress on things like empirical mechanistic anomaly detection, because you can just solve it by doing a bunch of stuff that is intuitively like seems unscalable or like wouldn't work in more complicated settings, or just like doing regularization or retraining your model or fine-tuning or whatever.
Sure.
I think I'm not very familiar with like what people mean when they say search for explanations. I think naively I mean the same thing as mechanism by what they mean as explanation, or like explanations are maybe sets of mechanisms in my head.
Yeah.
Not quite sets, but like mechanisms layered on top of each other. And I think it would be reasonable to ask questions like, when your explanation of your model's behavior has like an or structure where it like could be doing A or B, we want to be able to detect like whether or not it's doing A or whether or not it's doing B on like any specific input. I think that's like a reasonable question to ask of explanations, and I would be like excited if someone did something related to explanations that enabled you to do that thing, or like defined explanations in a way that made it sort of possible to do that sort of thing, etc., etc.
Okay. Cool. So perhaps speaking of explanations, I maybe want to move on to this paper that is called Formalizing the Presumption of Independence, authored by Paul Cristiano, Eric Nyman, and yourself in, I guess it was on Archive November last year.
Yeah,
sounds
around then.
Cool. So yeah, for this paper, can you tell us, for those who haven't heard of it, what's the deal with it?
Yeah, so I think ARC's work right now is roughly divided into two camps. One camp is like, given some sense of what a mechanism is or what an explanation is, how can we like use that to do useful stuff for alignment, under which like mechanistic anomaly detection is sort of the main angle of attack there.
Yeah.
And then there's the other half of ARC's work is like, what do we mean by mechanism, or like what is a mechanism, what is an explanation? And that is largely what formalizing the presumption of independence is. And so formalizing the presumption of independence more specifically is about, okay, so suppose you have a list of quantities like A, B, C, D, E, etc., and you're interested in the product of these quantities. And you knew, for example, like expectation of A, expectation of B, expectation of C. I claim a reasonable thing to do is to assume that these quantities are independent from each other, to presume independence, if you will, and say that expectation of A times B times C times D equals expectation of A times expectation of B times expectation of C times expectation of D. And this is quote unquote like a reasonable best guess. And then there's some question of like, okay, but then sometimes in fact A is correlated with B and C is correlated with D. And so this guess is wrong. And so we want to be able to sort of make a best guess about how various quantities are related, presuming independence, But then if someone comes to us and is like, hey, actually, if you notice that A is correlated with B, we want to be able to like revise our guess in light of this new knowledge.
Right.
And so formalizing the presumption of independence is about sort of the quest to define these two objects that are related in this way. So we have a heuristic estimator, which we want to quote unquote like presume independence. And then we want a heuristic argument, which is an object that we feed to a heuristic estimator to be like a list of ways in which the presumption of independence is false. And like actually you should be tracking the correlation or maybe higher order analogs of between various quantities. So we can imagine that, for example, by default, given A times B, your heuristic estimator will estimate expectation of A times B as expectation of A times expectation of B. And then you can feed it a heuristic argument, which is like, could be of the form like, hey, actually A and B are correlated, or like, hey, actually you should track the expectation of A times B, which will make your heuristic estimator like more exact and calculate expectation of A times B as maybe expectation of A times expectation of B plus the covariance between A and B, which is the correct answer. And then we want to be able to do this for everything, I guess, is the simple answer there. So we want to be able to say, given an arbitrary neural net, we have some default guess at the neural net, which is maybe that we just assume that everything is independent of everything else. So we want a default guess for like the expectation of the neural net on some compact representation of the data distribution, which we often call like mean propagation, where you just take the means of everything, and then when you multiply two quantities, you assume that the expectation of the product is the product of the expectations, and you just like do this throughout the entire neural net.
Yep.
And this is going to be probably pretty good for randomly initialized neural nets, because randomly initialized neural nets like in fact don't have correlations that like go one way or the other. And then you have to add the ReLUs. That's a bit complicated. Let's assume for now there are no ReLUs, and instead of ReLUs we just square things, and then it's kind of more clear what to do. But then again, your guess will be very bad, because like if you have an expectation 0 thing and then you square it, you're going to be like, well, the expectation of the square is going to be the product of the expectations, and so it's probably 0.
Yep.
But actually it's not probably 0, because like most things have some amount of variance.
Yep.
And then hopefully someone can come in, or ideally we'll have a heuristic estimator that does this by default, and then someone will come in with a sort of list of ways in which this presumption of independence is not very good. For example, the square of things is often positive, or like things often have variance, and then we'll be able to sort of add this to our estimate, and we'll be able to do like a more refined version of mean propagation, where you keep track of like various covariances between things and higher order analogs of. And then hopefully we'll be able to do that. And I think there's a bunch of follow-up questions, which is like, why is this useful? Why do you think this is possible? Yeah, maybe I'm happy to go in the order that you think is best.
Sure. So, first of all, so my understanding is that this is related to the mechanistic anomaly detection paradigm, where I think the thing is supposed to be that like a heuristic argument is a mechanism, or is playing the role of a mechanism. Is that right?
I think it's more accurate to think of heuristic arguments as like lists of mechanisms. I think like that is also not quite right, and the entire paradigm is like a bit not, or like the words are not good, because I think there's going to be no such thing as like one mechanism as distinct from other mechanisms. I just think like it's going to be an entire layered mess of like different mechanisms constantly interacting with each other, et cetera, et cetera.
Right.
Or it's like kind of hard to point to like any computer program and be like, there are 7 distinct mechanisms for why the program is behaving as it is. There's just like one thing, and then it splits into 2 things, and then it like interacts with the third thing. And so you probably won't have this like list of distinct mechanisms, but the idea is that a heuristic argument is like a set of mechanisms, or like a set of mechanisms plus ways that they relate to each other, et cetera, et cetera.
Yeah.
And the hope is that like this is the kind of object that we'll need to be able to do mechanistic anomaly detection.
Yeah, like if the old arguments for why your network is outputting be nice is different from the new argument for why your network is outputting be nice, then you should be like as worried as if there were different mechanisms, like something like that.
Yeah. Or the hope is to just use the heuristic estimator plus heuristic argument in like all of the schemes that I was describing previously. Like you have a heuristic argument for why your model is behaving the way it is, or like your heuristic argument explains like 99.9% of the variance of your model during training, and then you ask whether or not like there exists any heuristic argument that explains 99.9% of the variance of your model during training, but like does not explain this particular data point off distribution. And then like if that ever happens, then you're like, this data point was using like a part of the model only responsible for like 1 in 1,000 parts of its variance during training. That's kind of weird. No good.
Right. Yeah, I guess and this is actually interesting because I don't know, one thing that I was thinking of when thinking about this is like in physics, you can often use these energy arguments, right? So here's a classic energy argument. You have some ramp, right? You have a ball at the like it's resting on the top of the ramp, and for convenience sake, like this ball, it's actually just like infinitely like it's a point particle.
Yeah.
It's like got zero radius. So you put it at the top of the ramp and then you let go. And then the bottom of the ramp is like horizontal.
Yep.
And at the end, like the ball's traveling at the bottom of the ramp, and you ask like, okay, how fast is the ball going at the bottom of the ramp?
Yeah.
And like there's this way you could argue it, which is like, well, you know, the height between the top of the ramp and the bottom of the ramp is this much. And so initially the ball had this like gravitational potential energy that it used up by like moving down. And then at the end, like the ball just has like kinetic energy, which is just its velocity. And then you're like, well, that's got to be equal because energy is conserved. And then you like, you know, back out the velocity of the ball. And like the interesting thing about this argument is that it doesn't actually rely on the shape of the ramp.
Yeah.
Or like what's like the ball could do like loop-de-loops in the middle and like bounce around, you know, bounce off a bunch of things. And like you'll still get the same answer. And so there are like a bunch of mechanisms that correspond to this argument of energy conservation.
Yeah.
But it seems like at some level, like as long as like you can have this argument that energy got conserved, that's qualitatively different from arguments where like I took the ball and then put it at the bottom of the ramp and then gave it the right amount of velocity.
Yeah.
Yeah. I don't know. That's not really a question, so you have the choice to react to that or not.
Yeah, so I think we often consider examples like this from physics, and the hope is that, like, maybe more abstractly, there's like a set of approximations that people often make when solving simple physics problems, like there's no air resistance, things are point masses, there's no friction, etc., etc.
Yep.
And the hope is that these all correspond to like uses of the presumption of independence. This is simplest for the ideal gas law, which is like where the presumption of independence when using the ideal gas law is like the like particles, their like position is randomly distributed inside the volume, like they don't interact with each other.
Yeah.
Like particles are independent of each other. They have no electrostatic forces on each other, and they have no volume also. And it's not immediately obvious to me what uses of the presumption of independence correspond to no friction.
I mean, I think it's not because so if I think about like no friction or point particle in the ramp example, right?
Yeah.
If you add in those assumptions, like those like systematically change that answer, or I don't know. I guess like those can only ever make your predicted velocity go down.
That's true.
They can never like increase your predicted velocity because like, you know, energy gets leaked to friction, or because like part of your energy is like making you rotate instead of like making you have a linear velocity. And that strikes me as kind of different from other cases where like if things can be correlated, well, they can be correlated in ways that make the number bigger or in ways that make the number smaller.
Yeah.
Usually.
Well,
except for the case of like you square something and like in that case when you add the covariance between x and x, that like always makes the expected square bigger.
Yeah, so I think there are going to be cases in general where adding more stuff to your heuristic argument will like predictably make the answer go one way or the other because you like looked at the structure of the system in question before like thinking about what heuristic arguments to add. I think like there are ways of making like one presumption of independence is like relative to the ball's center of mass, the like position of the various bits of the ball is like independent or something. Whereas
Mm.
if balls are actually rotating, or like the velocity of the bits of the ball is independent,
Right, right.
or like zero, maybe. But actually, balls rotate sometimes. Or like, I actually don't know about the friction one. I guess balls don't have that much friction. But it's like you can assume that the like bits of the ball don't exert any force on like the bits of the ramp or whatever.
Yeah. Or you could imagine maybe the maybe the ball rubbing against the ramp causes the ramp to push the ball even harder.
Maybe. I think that's hopefully not going to be a valid use of the presumption of independence, but I'm not quite sure.
Yeah. Or I guess I'm just like it could slow the ball down or it could speed the ball up and like
If you were truly
maybe
naive looking at physics,
yeah.
you would be like, who knows what's going to happen when you add this interaction term.
And in fact, like modeling friction is actually kind of tricky. Like it's you get told like, oh, friction, but like wait, what is friction? Like
Yeah. But yeah, I think these are the kinds of things where heuristic estimators are hopefully quite useful. Or like there's some intuitive question or problem, which is like there's a ball at the top of the ramp. What is its velocity going to be at the bottom of the ramp? And oftentimes the actual answer, or like the actual answer is like, I don't know. There's a trillion factors at play.
yeah.
However, you can make this energy argument that's like a pretty good guess in a wide range of circumstances. And you're like never going to be able to prove basically that the velocity of the ball is going to be a certain thing at the bottom. I guess prove is kind of complicated when you're talking about the physical world, but if you suppose that you have like a computer simulation
Yeah.
with like all the little particles interacting with each other, basically the only way that you're going to prove that the ball ends up at the bottom with a certain velocity is like to exhaustively run the entire simulation forwards and like check at the end what its velocity actually is. However, there's this like kind of reasoning that seems like intuitively very valid, which is like assume the air doesn't matter, assume the friction doesn't matter, just calculate the energy and do that argument, that we sort of want to be able to capture and formalize in this concept of a heuristic estimator. And then the heuristic argument will correspond to like consider the energy. And then maybe if the friction is actually, maybe if there's like lots of wind, then in fact the air resistance on the ball is non-negligible, and then you can add something to your heuristic argument, which is like also you got to consider the fact that the wind pushes the ball a little bit.
Hmm.
And then your estimate will get more accurate over time, and hopefully it'll be a big good time. I don't know.
Yeah, yeah.
Hopefully it'll work.
And interestingly, like, yeah, the wind pushes the ball is saying that like the interactions between the wind and the ball are not zero mean, or like there's some covariance or something.
One should notice these things to
Yeah.
get a better estimate. Yeah. And so hopefully we'll be able to do this for like everything. We'll be able to do it for like all the physics examples, and there's a set of math examples that I'm happy to talk about. And then obviously the application we truly care about is the neural net application.
Yep. Yeah, speaking of examples, so in the paper, you have a bunch of examples from number theory.
Yeah.
Or there are also some other examples, but like to be honest, it seems like the main victory of these sorts of arguments is in number theory, where you can like just imagine that primes are randomly distributed and like make a few facts about their distribution and just like deduce a bunch of true facts. So what I'm wondering is like outside number theory. So you give some examples where heuristic arguments like do kind of work.
Yeah.
Are there any cases where you've had like the most difficulty in applying heuristic arguments?
Yeah. So I haven't personally spent that much time looking for these examples. Yeah, so we are quite interested in cases where heuristic arguments give quote unquote the wrong answer. I think this is a bit complicated. And so the reason it's a bit complicated is like there's this nature of a heuristic argument is to be like open to revision. And so like obviously you can make heuristic arguments that give the wrong answer. Like suppose A and B are correlated and I just don't tell you to notice the correlation, then you're just going to be really wrong. And so it's kind of unclear what is meant by like a heuristic argument that gives the wrong answer. And so we often search, there's like two sorts of things that we're interested in. One sort of thing is like an example of a thing that's true, or like an example of an improbable thing that happens way more likely than you would have naively expected, that seems to happen for like quote unquote no reason, such that we like can't find a heuristic argument in some sense. So obviously you can find a heuristic argument if you just exhaustively compute everything. And so there's some notion of length here where we can't find like a compact heuristic argument that seems to describe quote unquote like why this thing happens the way it does. Where we conjecture that it's always possible to like explain a phenomenon in roughly the same like length of the phenomenon itself. And then another thing that we search for often is we want to be able to use heuristic arguments for like this sort of mechanism distinction problem. And so we search for examples of cases where heuristic arguments have this structure where it's like A happens, therefore B happens, and sometimes C happens, therefore B happens, but you can't distinguish between A and C efficiently. So I can talk about those examples, or I can talk about, so I think the closest example we have of something that seems like kind of surprising, but not like we don't quite have a heuristic argument is like, so you have Fermat's last theorem, which states that a to the n plus b to the n equals c to the n has no integer solutions for n greater than 2.
Non-trivial integer solutions.
Non-trivial
You
integer
get 0
solutions.
and 1, but yeah.
Well, 1 doesn't quite work because 1
0 to the n plus 1 to the n equals 1 to the n.
Oh, sure, yeah.
Yeah.
And so the n equals 4 and above case, the heuristic argument is quite simple, where you can just assume that like the fourth powers are distributed randomly with their respective intervals or whatever. There's like, n fourth powers between 1 and n to the 4, and then you can just like assume that these fourth powers are distributed independently, and then you correctly deduce that they're going to be like vanishingly small solutions to this equation. And then I'm not like that familiar with the details here, but the n equals 3 case is like kind of interesting. And in fact, the heuristic argument for the n equals 3 case is like basically the same as the proof for the n equals 3 case, because the way the numerics work out for the n equals 3 case is if you do this naive assumption, there's going to be like infinite expected solutions.
Yep.
And then there's like a complex structure in the equation itself that suggests that all the solutions are like correlated with each other. So either there's going to be like a lot of solutions, or there's going to be like basically none solutions.
Yep.
And then you like check. And in fact, there's going to be like basically none solutions, or basically 0 solutions. And the heuristic argument for this fact is basically the proof of this fact, which is like quite long. But the problem is like the solutions are, you also heuristically expect the solutions to be very sparse. And so you're like not that surprised that you haven't found a solution until you've checked like a lot of examples or a lot of numbers. And so like the number of things that you have to check is large such that you can like fit the heuristic argument. So you're like not that surprised. I don't know if that made that much sense.
Yeah, that makes some sense. So I don't know. It's sort of like this case where heuristic arguments, it's like they're not winning that much over proof.
Yeah, or it's like it like almost didn't fit, but like the phenomenon you were supposed to be surprised by was like barely not surprising enough, such that you like had enough room to fit the argument in before you got too surprised, such that you would like expect there to be an argument or something. I don't know. It's kind of unclear whether or not that should be like evidence in favor of our claim or against our claim that there's always heuristic arguments. Because like in fact there is a heuristic argument in this case, but it like maybe barely wasn't, or maybe like barely wasn't a heuristic argument.
Right.
And so it's like kind of confusing,
One thing that I found myself wondering was like, it seems like you have this structure where you have this list of facts, and you're wanting to get a heuristic argument given this list of facts.
Yep.
Right. And in the paper, you describe this cumulant propagation thing, which basically just involves keeping track of like expectations and covariances and some higher order things. You pick like some level that you want to keep track of, and you do that. But then like you mentioned like some failures of this approach and like some ways you can fix it. One thing that like kind of struck me as the obvious first approach is like, just having a maximum entropy distribution given some facts.
Yeah.
So for people who don't know, this is this idea of like, you have some probability distribution over some like set of interest, and you don't know what your probability distribution is, but you know that it's got to have like this average and this, correlation between these two things and this covariance. And basically you say, well, given that I only know these things, I want to maximize the entropy of my probability distribution. So like my probability distribution has to satisfy these constraints, but I've got to be like as uncertain as I can possibly be given those constraints. And so this is like a big thing in Bayesian reasoning, and intuitively it seems like it would fit this thing. Like every time you hear a new fact, you can like add a constraint to your, and like now get a new maximum entropy distribution. It always gives answers. I remember in the discussion of cumulant propagation, you mentioned some cases where maximum entropy would do better than it does, although I don't remember the exact reason why. I think it was something to do with like calculating the square of some quantity is negative in expectation.
Yeah.
So why not just do maximum entropy?
Yeah. So historically, we've considered a lot of maximum entropy type approaches, and all of them were a bit unsatisfying. So I think there's like 3-ish reasons that we think maximum entropy is sort of unsatisfying in various ways. I think the first one is perhaps most compelling but most naive, and I'll give that example first.
Okay.
So suppose that you have A and B, and then you're taking the AND of A and B. So suppose we have C equals A and B.
Yep.
And suppose that we know like C is 50-50. Then the maximum entropy distribution on A and B, given C is 50-50, So if we condition on C being 50-50, the maximum entropy distribution over A and B has like A and B correlated a little bit, but also it raises the probability of A and it raises the probability of B.
Relative to
50-50.
Okay.
And there's like various reasons why this is unsatisfying. The sort of obvious, or the main reason I guess it's unsatisfying is like, suppose you have a circuit that is computing some stuff, and then you just add a bunch of like auxiliary gates where like you have some wires, and then you pick 2 wires and you're like, I want these wires to be correlated. Then you can just add the AND of those wires like a bunch of times to your circuit. And then if you want the maximum entropy distribution over all the wires, it will like want to push the AND of those 2 wires down to 50-50, because that's like the maximum entropy probability for a wire to be. And so it will like induce this fake correlation between the wires while you're trying to do that.
Sorry, hang on. Wait. So was it the case that the desired... So just going back to the A, B, C, which is A and B thing.
Yeah.
Is the idea that like the thing you wanted was for A and B to be uncorrelated, but like have, high enough probability that like when you combine them to get C, the probability of C being true is 50-50?
I think I actually explained the example wrong. So suppose you just have your circuit is just 2 wires. It takes 2 inputs and it just outputs both of them.
Yep.
Then you're like, the maximum entropy distribution is 50-50 over both wires.
Yep.
That seems correct. And then suppose you just randomly added an AND gate. Then the maximum entropy distribution would
So when you say randomly added an AND gate, you mean like you have your 2 inputs and then you put an AND gate that takes your 2 inputs.
Yeah.
And the output of that gate is your new output.
No, you don't connect it to the output at all. You still output A and B, but you've just like added an AND gate as some auxiliary computation that your circuit does for no reason.
Okay.
Then if you want to take the maximum entropy distribution over like all the things your circuit is doing, then adding this gate will like artificially raise the probability of A and B and also induce this correlation between A and B.
Why?
Sorry. So naively it won't, because your maximum entropy distribution will just be like A, B, C, all 50-50 and independent.
Yep.
And then suppose someone came to you and was like, actually, you need to respect the like logical structure of this circuit. C can only be on if A and B are both on.
Yep.
The probability of C being on has to be like the probability of A being on times the probability of B being on plus like the interaction term.
Yep.
Then you will get this induced correlation between A and B, plus A and B will like be raised to like 0.6 or whatever.
So is the idea that you have this like intermediate thing in your circuit, and you have to be maximum entropy also over this intermediate thing. And so even though you didn't really care about the intermediate thing, like it didn't play any role of interest in anything else, because you're like being maximum entropy over that, Like you've got to like mess around with the distributions over other variables.
Yeah, that's right. And I think of this as a special case of a more general phenomenon where like there's this like computation that you're doing throughout the circuit, and you can pretend there's some notion of like time in your circuit where like or gates that only take input wires as inputs are like at time one, and then if you like take an input as in a gate that took itself inputs as input, then that's like time two, et cetera, et cetera.
Hmm.
Or like you're going down your circuit and computing things. And maximum entropy distributions have this property where like things that you compute in quote unquote the future like go back in time and like affect the past.
In the sense of like once you know things about the future, that gives you constraints on the past.
Yeah. And if you want to be maximum entropy, it like causes you to mess with your probabilities of like the input wires. If you learn that like you're computing lots of ands, then you like want to raise the probability of your input wires, et cetera, et cetera. And I think this is like in general going to be kind of an undesirable property. And it's a bit complicated to talk about why it's undesirable. I guess the simplest reason is like someone can mess with you by like putting a bunch of stuff at the end of your circuit. And then like once you get to the end of your circuit, you're like forced to go back and revise your initial guesses.
Yeah.
Whereas it seems like intuitively heuristic arguments want to be like more deductive in nature, where you like start with some premises and then you like deduce facts from those premises, and like nothing anyone can say after you've started with your premises, or like nothing anyone can add to your circuit after you deduce facts from your premises can like cause you to go back in time and be like, actually my premises were wrong, because that like I don't know, it doesn't really make that much sense that like if you assume that A is 50-50 and B is 50-50, and then you're like, I'm computing C, which is A and B, I guess A and B are like 60-40 now, and they're also slightly correlated.
Yeah.
Or like that kind of reasoning seems like intuitively invalid. And it's the kind of reasoning that like various forms of maximum entropy force you to take. And you can try to do various other stuff to like eliminate this problem, which we've explored historically. And I think like none of them seem that satisfying and like fix the problem that well or something.
Right. Okay, that's a useful response. Like you just end up with these like useless variables that you shouldn't have cared about the entropy of, but you do now. So this relates to this question I have about like the robustness or the adversarial robustness of these like maximum of these heuristic estimators.
Sorry, maybe we want to. So I said originally that there were like three reasons why we didn't like maximum entropy.
Yeah.
I'm happy to talk about the other two also, but maybe we don't. Maybe you don't want to.
Yeah. Or I think I'm sold by reason 1. If you want to talk about reason 2 and reason 3, like I'm all ears.
Yeah. Well, so I think they like are somewhat related to this more general problem of like why heuristic arguments are going to be possible to begin with. Yeah. So I think reason 2 is going to be something like we can't actually maintain full probability distributions over things.
Hmm.
So there's an important thing a probability distribution has to be, which is like consistent with various facts or something.
Hmm.
Like it has to be a real probability distribution. It has to describe like actual things that are realizable. And I think heuristic arguments or your heuristic estimator like can't be real in that sense. Like your distribution over possible states your circuit can take can't be like a distribution over actual possible states your circuit can take. So one reason that we sort of want this is like some of our mechanistic anomaly detection applications have us believing things like A is on and B is on, but A and B are not on, because we want to be able to like drop out mechanisms, and you just straight out can't do that if you have an actual probability distribution over actual outcomes, because like A being on and being on must imply that A and B is being on.
Hmm.
And the second reason is like in terms of just computational complexity, it's very likely just going to be impossible to like actually have a distribution over realizable or like physically possible or logically possible states,
Right.
because like the act of determining whether or not something is logically possible is very hard. I think Eric Nyman has a couple of neat examples where it's just like various circuits where it's like sharp p hard to determine or to like have a distribution over like actual states that are satisfied by that circuit, although I'm not familiar with the details enough to talk about them here.
Okay.
And then there was some third reason, which I'm forgetting.
Okay, cool. So, yeah, one thing that I'm wondering about is like, you mention in the paper that it's difficult to get adversarial robustness. Like there are various reasons you think that you should be able to be fooled by like, people adversarially picking bad arguments to phase. So often in the AI realm, when I hear that something is vulnerable to adversaries, I'm really worried because I'm like, well, what if my AI is an adversary? I'm wondering, do you think that this worry applies in the heuristic arguments case?
Yeah. So first, I guess I'll talk about situations in which I think it's basically impossible to be adversarially robust. Yeah. So suppose you have a hash function that gives like -1 or 1.
Yep.
And you're estimating the sum of like hash of n over n squared.
Mm.
And suppose your heuristic argument can just like point out the values of various hash terms. So your naive heuristic estimator, presumption of independence, like 50-50 between 1 and -1, so the estimate's 0.
Yep.
And then your heuristic argument consists of like pointing out the values of various hash terms.
Yep.
In this situation, there's just like always going to exist arguments that like continue to drive you up or continue to drive you down.
Yep.
And someone's always going to be like, hey, hash of 2 is 1, hash of 7 is 1, hash of 9 is 1, and you're just going to be driven up and up.
Yep.
It's possible it should be like hash of n over n to the 1.5 or something to make it bad. And so you're in this kind of awkward spot where for any quantity with like sufficient noise, even if you expect very strongly the noise to average out to 0, there will exist a heuristic argument that like only points out the positive values of the noise and will like drive you up, or there exists a heuristic argument that only points out the negative values of the noise and drive you down. And so I think this is like naively quite a big problem for like the entire heuristic argument paradigm. If you're ever relying on something like someone doing an unrestricted search for heuristic arguments of various forms and like inputting them into your heuristic estimator. So there's like a couple way outs. First, I'll talk about the like simplest way out that I think ends up ultimately not working, but is worth talking about anyway. I think the simplest thing you can do is just have two people searching for heuristic arguments, one person driving them up and one person driving them down.
Yep.
Yeah. So hopefully, if you have one search process searching for heuristic arguments to drive you up and one to drive you down, then we don't like systematically maybe expect one person to be biased instead. I think this is a problem. For example, so like one obvious thing to do is both players have like equal amounts of time to find heuristic arguments or something.
Yep.
However, if you consider the previous case with hash of n, suppose instead of being like 50-50, 1 and -1, hash of n is actually like 1/4 1, 3/4 -1.
Yep.
Then in that case, the like player finding heuristic arguments to go down has like a 3x advantage over the player finding heuristic arguments to go up. And so then you're like no good, because you can have these quantities where it's like far easier to find heuristic arguments to drive you up than to drive you down, or vice versa.
Yeah. Although in that case, you really should be below 0 in expectation, right?
Yeah.
Yeah, I think there's some example in the paper that people can read where it really checks out that debate is not going to work.
So you have examples like that make you very sad. And so instead of doing debate, we want to do this other thing that's going to be kind of interesting. So if you imagine being like searching for heuristic arguments in the setting where you have like hash of n over n to the 1.5 or whatever, the way that you're going to do this is you're going to like first check hash of 1, then you're going to check hash of 2, and then you're going to check hash of 3, etc., etc. And suppose that you wanted to drive the estimate of the quantity up. Then you would like check hash of 1, and suppose it's positive. You're like, great, let's include term 1. And then you check hash of 2 and it's negative, and you're like, okay, let's not include term 2. And then you check hash of 3 and it's also negative, and you're like, let's not include that. Check hash of 4, it is positive, so then you include that. Yeah. And you're like carefully going through these terms and eliminating the ones that are negative. However, the interesting thing is like if you imagine being the person that's doing this, there in some sense exists like a broader heuristic argument that you first considered and then pruned down, which
Yeah.
is like you know the values of all these four terms, and then you selected the terms that were only positive.
Yeah.
And so there's some sense in which if instead of including only the heuristic argument that you produced at the end, you included like the entire search process for the heuristic argument, and also I guess the heuristic argument you included at the end, then hopefully the heuristic estimator is like forced to be like, well, we actually looked at all four of these terms and then we discarded two of them. But like the discarding part isn't relevant because I already like know all four of these logical facts. So I'm like forced to include all four of these terms.
Mm.
And so then the hope is not that there doesn't exist heuristic arguments that are misleading, but there's no like way of searching for heuristic arguments that's systematically misleading if you don't like already know the values of the heuristic arguments. And this is kind of related to like the presumption of independence being quote unquote like correct on average or something. And so like if you're presuming independence where in a way that's like correct on average, then on average people can only like when searching for arguments and just like looking at stuff, they can only like lead you closer to the truth, hopefully.
Sure. So the idea is that like if in some sense we can like, well, like we should be able to have some broad search process over arguments that essentially isn't adversarial and use that.
Yeah.
It sounds like is the upshot.
Well, it's like even if the search is adversarial, if you're conditioning on everything that the search process like knows while it's searching, then
Right.
it like can't be adversarial because all it can do is like look at values, and it's like it doesn't know what the value is before it looks. And if you've like actually presumed independence
Sure.
correctly, then on average everything it looks at has like an equal chance of driving you up or down.
Yeah. I mean, I guess I have this concern that maybe like the point of mechanistic anomaly detection was to help me know how to like elicit this latent knowledge or something. And so like I might have been imagining like using some AI to like, come up with arguments and like tell me that the thing was bad. And like if I'm using that AI to help me get mechanistic anomaly detection, and I need mechanistic anomaly detection to help me like get that AI be good, then well, that's some sort of recursion. It might be the bad type of recursion. It might be the good type of recursion where you can like bootstrap up, I guess.
Yeah, I think it's not very clear to me how this is ultimately going to shake out. I think this kind of adversarial robustness, or like how we deal with adversarial robustness, is like kind of important. I think there are like other ways out besides the way I described. I think like that's intuitively what we want to do, is we want to just like condition your heuristic estimator on like everything, even like the search for the arguments, and also I don't know, just all the things. And like
Yeah.
hopefully if you don't like let any adversarial selection into your heuristic estimator, then it like can't be adversarially selected against or something.
Yeah.
Like in some sense, so there's like a thing of if you're like a proper Bayesian and someone's like adversarially selecting evidence to show you,
Mm.
the thing that's supposed to happen is eventually you're just like, and now I think I'm being adversarially selected evidence to show, and I know this fact, and so I'm just like being a Bayesian, and then you just update on that fact, and you just like
Yeah.
aren't wrong on average if you're correct about the kinds of ways in which you're being adversarially selected against.
Yeah. Although it does require you to like, I don't know. I feel like this is a bit of Bayesian cope. Like cuz like in order to do that, like when you were a Bayesian, right? You were supposed to be like, "Oh, I'm just going to get observations and update on observations."
Yeah.
But now you're like, "Oh, well my new observation is that I'm observing that observation and maybe the observation process is weird."
Yeah.
But then I feel like, okay, like you've got this layer and like after that layer you just trust it, and before that layer you like worry about like things being screened or whatever. And I'm like, okay, where do you put the layer? Like you had to enlarge your model to like make this be, I don't know, it seems a bit.
Yeah. I mean, yeah, I think being a Bayesian is hard, but like the thing we're going to try to do is like just look over the shoulder of the person selecting the evidence to show you, and then see
Yeah.
everything that they see, and then hopefully they're not like misled on average because they're just like looking at stuff, you know?
Yeah. In that case, it's better than I think the Bayesian case. Or I don't have the same complaints as I have about the Bayesian case. So stepping back a bit, there are like a few different ways that somebody might have tried to concretize a mechanism. So
Yeah.
there's this one approach where like we have something called a heuristic argument, and like we're gonna work to try and figure out how to formalize that. I guess we haven't explicitly said this yet, maybe, but like in the paper, it's like still an open problem, right?
Yeah. Or we
Um,
have like,
there are
here,
avenues, but
yeah. I guess I would say we have some heuristic estimator for some quantities that are like deficient in various ways, and we're trying to like figure out what's up and get better ones for other quantities and then unify them. And
yeah,
hopefully all the dominoes will like fall over once we quest sufficiently deeply.
nice. So there's this approach. There's also some people working on various like causal abstractions. So like causal scrubbing is like work by Redwood Research. There's other causal abstraction work by other groups. I'm wondering like how do you think out of the landscape of all the ways in which one might have concretized what a mechanism is, how do you think like how promising do you think heuristic arguments is?
Yeah, so I'm tempted to say something like if the causal abstraction stuff works out, we'll just call that a heuristic argument and go with that sort of thing. Or
Okay.
like heuristic arguments is intended to be this sort of umbrella term for like this sort of like machine checkable proof like thing that can apply to like arbitrary computational objects. And I think like that's what I'm tempted to say. I think in fact we do have like various desiderata that we think are like important for our particular approach to heuristic arguments, and we want them to be like proof like in various ways that e.g. causal abstractions often aren't, or we want them to be like fully mechanistic and have like zero empirical parts in them, whereas often various causal abstraction approaches allow you to like measure some stuff empirically and then like do deduction with the rest of it. I think like I very much think of us as like going for the throat on this sort of heuristic argument stuff. Like there's some question you might ask, which is like, why do you expect heuristic arguments to apply to neural nets? And the answer to that is like, well, neural nets are just a computational object, and we want to have heuristic estimators that work for like literally all computational objects. And then the reason why it applies to neural nets in particular is just because like neural nets are a thing that you can formally define. Whereas there's a lot of more restricted approaches to like explanations that are like, well, we only actually care about the neural net thing, and so we ought to like define it in particular about the neural net thing and stuff like that.
Hmm.
Yeah, so maybe in summary, we're trying to be like in some sense maximally ambitious with respect to the existence of heuristic arguments.
Gotcha. So I'd like to move on a little bit to sort of the overall plan. So I think in some of these early posts, the idea is like step one, formalize heuristic arguments. Step two, solve mechanistic anomaly detection given a formalism of heuristic arguments. And step three, find a way of finding heuristic arguments. And really, I guess like these three things could sort of be run in parallel or,
Yeah.
not necessarily in order. I'm wondering, like, the last sort of batch of publications was in like late 2022. How's the plan going since then?
Yeah, so I think like Q1 of 2023 was a bit rough and we didn't get that much done. I think it's sped up since then. So I can talk about stuff that is, yeah, so things that I think are good that have happened. We have a pretty good formal problem statement about what it means to be a heuristic estimator for like a class of functions or like a class of circuits that we call bilinear circuits where just all your gates are squares.
Mm.
So we have that desiderata, and we can talk about like what it means to be a good heuristic estimator with respect to that class of circuits in a way that things we think are good satisfy, or like some stuff we have satisfies and some other stuff we have doesn't satisfy. So hopefully that's just like a fully formal problem. We have a better class of heuristic estimators for cumulant propagation, or like we have an upgrade on cumulant propagation that we call reductant propagation, which is like it's just like slightly different. Instead of keeping track of cumulants, you keep track of like a different thing called a reductant, and it's like slightly better in
Okay.
various ill-defined ways, but it's like more accurate empirically on on like most distribution of circuits we've tried, et cetera, and we like feel better about it. We have like a clearer sense of what it means to do mechanistic anomaly detection and like how that needs to go and like what the hard cases are going to be for doing mechanistic anomaly detection in terms of like being unable to distinguish between mechanisms. Yeah. I notice I didn't really answer your original question, which is like, how's it going? I think it's like going par or something.
Okay. So
Maybe
like
like
there's
maybe Q1 was like slightly below par and like we're doing slightly above par in Q2. And so it's like on average par or something.
so par in the sense of like you've gotten like a better sense of some of the special cases, like not yet knocked totally out of the park, but like
Yeah. Or like if you told me that this is how much progress we would have made at the beginning of 2023, I would be like, okay, that seems like good enough to be worth doing or something. Let's do that. Or
all
like
right,
this is how we should spend our time or something.
cool. I'm wondering, yeah, given that progress, so out of the steps of like formalize heuristic arguments, solve mechanistic anomaly detection, given that, and find heuristic arguments, how optimistic are you about the steps? Which ones seem like most difficult?
Yeah, so I think the thing that's most difficult is formalizing heuristic arguments in a way that makes them findable. Like, here's a formalization of heuristic arguments, they're just proofs. Um,
Yeah, yeah.
and so there's some sense in which heuristic arguments and find like heuristic arguments being like compact is like intrinsic to the nature of what it is to be a heuristic argument. I think like doing useful stuff with heuristic arguments is pretty unlikely to be the place where we like fall down. I think it's kind of possible that heuristic arguments get formalized and then we're like, darn, we can't do like any of the things that we thought we were going to be able to do with heuristic arguments because it turns out that they're like very different than what we thought they were going to be like.
Hmm.
I think that would be like pretty good though, because we would have heuristic arguments and we would like in some sense be done with that part. And then it would be very surprising to me if they were like not useful in various ways. I don't know if that was a complete answer.
I think that worked. I'm wondering like if there's been any experimental work on trying out mechanistic anomaly detection things beyond the. So I guess you've mentioned like there are various interpretability things that you think like won't scale. Is there any like promising experimental work you're aware of?
Yeah, so I am not very aware of experimental work in general, but I think Redwood is currently working on what they're calling like elk benchmarks,
Hmm.
where they're trying to do this sort of mechanism distinction on like toy problems like function evaluation. I don't know how that's going because I am not up to date on details.
Fair enough.
I think like ARC employees often write code to like check whether or not heuristic estimators do some things or like check how empirically accurate they are or like find counterexamples by like random search or something. Probably you don't want to call that like experimental work because we're just like checking how accurate our like heuristic estimators for permanence of matrices are or whatever.
Hmm.
Yeah. So I think the short answer is like I think Redwood's doing some stuff that I don't know that much about
Okay.
and I'm not really aware of other stuff being done. But that is probably mostly because I'm like not that aware of other stuff and not because like it's not being done. Although it probably also isn't being done in the way that like I would want it to be done or whatever.
Gotcha. Yeah. So it's about time for us to be wrapping up. Before I close up, I'm wondering if there's any question that you think I should have asked.
I think like people often ask for probabilities that these sorts of things all work out, to which I often say like 1/7 that everything works out roughly the way that we think it's going to work out and
Okay.
is super great within 5 years ish. Maybe not quite 5 years now because I've been saving like 1/7 over 5 years for more than like a few months. So maybe it's like 4.5 years now. But other than that, I don't think so.
Okay. Fair enough. So finally, if people are interested in following your research, or if we have bright minds who are perhaps interested in contributing, what should they do?
Yeah, so ARC posts blog posts and various announcements on our website, alignment.org. And we're also currently hiring, so you can go to alignment.org and click the hiring button and then be directed to our hiring page.
Great. Well, thanks for talking to me today.
You're welcome. Thanks for having me on.
This episode is edited by Jack Garrett, and Amber Dornase helped with the transcription. The opening and closing themes are also by Jack Garrett. Financial support for this episode was provided by the Long-Term Future Fund, along with patrons such as Ben Weinstein-Rowan, Tor Barstad, and Alexei Malafeyev. To read a transcript of this episode, or to learn how to support the podcast yourself, you can visit axrp.net. Finally, if you have any feedback about this podcast, you can email me at feedback@axrp.net.